Okay, thank you so much for the invitation. I've really enjoyed listening to the talk so far, and I'm really happy to be here. I'm going to change gears quite a bit and talk about my work using coastal stratigraphy, sediments, and microfossils to reconstruct earthquake and tsunami records over the Holocene, so beyond the historical and the instrumental period, and get a better idea of the hazards we face along the coast. So why is this work important? Well, our historical and our instrumental records of earthquakes and tsunamis are temporally restricted. In the best case scenario, we have maybe 200 years of historical records, but as you go back in time, these records become quite spatially limited and difficult to interpret. Our instrumental records are even shorter. This is an issue because the recurrence interval of the largest and most destructive subduction zone earthquakes and tsunamis can be much longer than that. And so if we rely on these short records, we can completely miss these large events. A good example of this is the 2011 earthquake and tsunami offshore of northern Japan. Prior to this earthquake, it was thought that the subduction zone in this area was segmented in such a way that would limit earthquake magnitudes to less than a magnitude 8. However, geologic evidence actually existed along the coast that suggested that tsunamis of the size that happened in 2011 had affected the coast. However, those hadn't been included in these hazards assessments. In 2011, we had the large magnitude 9 earthquake, high tsunami that exceeded all expectations. As you can see in this picture, we had seawalls that had been built with this segmentation in mind that were overtopped. And you can really see the impact of not being prepared for these events. So what we really need are these geologic data sets on centennial and millennial timescales that can give us a much better idea of the spatial and temporal variability of ruptures and prepare us for future hazards. And so just to tie this into this theme of sustainability here, these geologic records are critical for building these sustainable coastal communities and infrastructure. So how can we take advantage of these opportunities along the coast? For example, in Japan, you had nuclear facilities along the coast. It's a strategic place, however, they weren't prepared to deal with tsunamis that affected that area. So how can we utilize and still protect these coastal areas? So how do we get these records of earthquakes and tsunamis in the coastal stratigraphy? It all starts with the earthquake deformation cycle, which is characterized by a period of interseismic strain accumulation, which you can see here. So we have our downgoing oceanic plate and our overriding continental plate. In the interseismic period, this is stuck, and it's accumulating strain, which is causing deformation both offshore, which is pulling the plate down, and onshore, which is slowly bulging the plate up. During the coast-seismic period, this strain is suddenly released, so you have the overlying continental plate popping up, causing uplift and displacing the ocean floor, creating a tsunami. And then along the coastline, you can get coastal subsidence on the order of meters that occurs during this coast-seismic period. So what we get then is this cycle, and this will then repeat itself because it's the earthquake deformation cycle. We get this cycle that's preserved in the coastal stratigraphy as a series of relative sea level changes. So in the interseismic period, you have the coastline gradually going down, which is causing a relative sea level fall. During the slowly going up, causing a relative sea level fall. In the coast-seismic, you have sudden subsidence of the coast, which is going to cause a sudden rise in relative sea level, which is then going to be recorded in these coastal environments over time. So what does this look like then in the stratigraphy? So if well, first of all, we need low energy depositional environments to capture these changes, right? We're not going to go and look at rocky coastlines because if you have an outcrop of rock that pops up or down, you're not going to really see that change in relative sea level. So we look for low energy depositional environments like coastal marshes and lagoons, estuaries, places that are sensitive to changes in relative sea level. So we need that accommodation space. So if we look at this cross-section here of a marsh, before coast-seismic land level change, we have this high marsh deposit happily forming, growing vegetation, accumulating sediment. During coast-seismic subsidence, the land suddenly drops down. Minutes to hours later, you have a tsunami that comes in. And then now you're going to have this persistent deformation of the coast. So this can last centuries as the coastline is dropped down and slowly accumulates that strain in between earthquake cycles again, and then develops another high marsh soil on top. And you'll see this repeated in the coastal stratigraphy. So this is a typical section that we find. We have this high marsh soil that's been suddenly subsided into the intertidal zone. If we're lucky, we get a sand bed on top, and then we now have changed the environment over centuries. We get a tidal mud, and then a gradual recovery back into this soil. So changes in stratigraphy like this can be created by other mechanisms in the marsh, such as tidal channel migration, reconfiguration of the estuary. So we have this set of criteria that we look for to try to argue that we are looking at a co-seismic event. First of all, we're on a subduction zone, so that's a likely mechanism. We look for sharp contact, so that's a sudden change of environment that you're not going to get from a gradual relative sea level change. We want to see a juxtaposition of environments, so you don't typically see a high marsh soil suddenly overlain by a mud. So this had to cause a, exceed the preservation threshold of meters, dropping down the marsh meters to get this change of environment. We look for them to be laterally continuous, so we can exclude these issues of a tidal channel migrating around, et cetera. And the best thing to be able to do is to correlate between regional sites. So if you can get sites that are kilometers apart that both show the same record, that you're then likely looking at a larger scale event and not a localized event. And if we're lucky, like I said, we find tsunami deposits, we don't always find them. So when we do find tsunamis, they have a distinctive look. So as a tsunami comes in, erodes the beach ridge, transports sediments inland. As it loses energy and decelerates, it's going to drop those sediments out of suspension. So we often see, on top of seeing this anomalous marine sediment, so this coarser grain sand bed in a low energy marsh environment, we also see landward thinning of the deposit and fining upward, showing that the sediment settled out of suspension. We find rip-up class, sharper eroded contact showing that high energy flow. And if we're lucky, we also have that land level change that's going to really support that we had an offshore rupture that created slip that affected the coast and created the tsunami and land level change. And we can then incorporate this sedimentary, this grain size data that we get out of these into inverse and forward models to reconstruct the flow speed of the tsunami and then take that and think about the offshore slip that caused that tsunami. Okay, so another really important component of these studies are microfossils, and I specialize in diatoms specifically. So diatoms are photosynthetic unicellular algae. They inhabit all aquatic environments, freshwater, brackish, marine, and they're really valuable in reconstructing paleo environments because of their preferences to a number of environmental factors. So they're very sensitive to changes in salinity, in substrate, in pH, et cetera. The list is long. For earthquake and tsunami studies, we utilize the salinity and substrate sensitivity the most. So if we look at this cross-section of a marsh here, we have our subtidal environment all the way up to our upland, and these are the different diatom groups that are distinctive of these different environments. And so in this subtidal environment, we have mostly planktonic diatoms that float in the water column, tolerate high levels of salinity. As we get higher in the tidal frame, we have our brackish diatoms, a lot of them attached to substrate like sand or mud. And then as we get even higher, we get diatoms that don't tolerate high levels of salinity at all and live attached to vegetation or on the surface of the marsh. And so these are really important because they can provide us with an independent test of our stratigraphic interpretations that we made from the changes in lithology that I mentioned before. So as our sea level goes up or down along the coast, these diatoms, pointers are difficult. Okay, these diatoms are going to respond to this change in salinity, change in inundation, and over time they're incorporated into the sedimentary record and provide this paleoenvironmental record of sea level basically along the coast. So in this same cross-section that I showed before, we can see that our diatoms throughout this sequence are in our high marsh deposit. We're going to start with our diatoms that live attached to plants, don't tolerate high salinity. During a tsunami, we generally see a mixed diatom assemblage because it washes over a variety of coastal zones and incorporates those diatoms and deposits them inland. Following the earthquake, we have the coast is now subsided and dropped down, so we have this really distinctive change in the diatom assemblage. They're going to be tidal flat diatoms, a lot of planktonic diatoms in that tidal flat deposit. And then gradually, they're going to shift back into that that low marsh environment and then back into the high marsh environment over time. So they can really be a powerful tool in capturing that full range of coseismic and interseismic deformation. And we can actually take that empirical relationship that I showed before in that marsh between the microfossil assemblages and their elevation in the tidal zone today, and we can get a number on that elevation of the assemblages today, and then go down core with that, find those same assemblages down core, and reconstruct the elevation that these diatoms must have been at the time they were deposited and grew there, and get quantitative estimates of coseismic subsidence. And that's been done a lot in Cascadia, for example, which can then lead to these 3D elastic dislocation models that can tell us about slip offshore and really characterize earthquakes over multiple earthquake cycles. In tsunami deposits, diatoms, obviously you're going to get this anomalous marine signature of your diatom, so it's going to tell us about the provenance of the deposit that we're looking at. Often they're low concentration because the beach sediments don't have a lot of diatoms in them, like an actual beach or beach ridge. High fragmentation, so as they're transported, we often see them broken up in the deposit. And we also can see sometimes the normal grading of the valves, just like we have the fining upward of the grain size of the sand, we also see fining upward of the diatom valves. Okay, so we've taken this kind of tool set and applied it all over the world. So I have a map here where I did a review of where diatoms have been applied in subduction zone paleoseismology studies around the world. These are just the papers that I've been on, so I've had an opportunity to travel around quite a bit and test out these methods. Today I just wanted to highlight one of our studies in Alaska to kind of show you from kind of start to finish how we go about doing the study and how we then take that data and really make the leap towards improving our understanding of hazards along subduction zones. So the Alaska Dilution subduction zone shown here, so here's the trench, here's Kodiak Island, here's Alaska itself and the peninsula. Prior to our work in this area, there really had been no paleoseismic studies to the west of Kodiak Island. So there's a lot of unknowns out here, even though we had had this series of historical ruptures that had occurred along the subduction zone. As you can see, the way they're distributed, they kind of suggest a segmentation along the subduction zone. But because our records are so short, we can't really say if this is a persistent segmentation or if it's just something because we have a low number of samples that we're looking at. So that's where our studies come in. So today I want to focus on this area between the Shumagon Islands and Kodiak Island. This is a very active part of the subduction zone. We've actually had one great earthquake here every 13 years, one 7 to 8 magnitude earthquake per year, and 6 to 7 magnitude earthquakes per year. So there's a lot going on here in comparison to Cascadia off the Pacific Northwest, where we have zero activity. So here the subduction zone is highly coupled, which means it's locked, like I showed in the intro slide. Those plates are locked and accumulating strain, and it's thought that this area could potentially create a large earthquake. Of particular concern in this area has been the Samiti segment of the subduction zone between the Shumagon Islands and Kodiak Island, because not only does this affect Alaska, but it orients tsunamis directly towards the California coast, specifically Southern California, because of the azimuth of the subduction zone here. So it's been on people's radar. The last earthquake on the Samiti segment was in 1938, which is here, but this rupture patch is a bit misleading because it didn't actually rupture the whole subduction zone interface, and it's thought that there's still some strain left there to release. 1964, which I'm sure everyone has heard about, magnitude 9.2, that was to the east on the Kodiak segment. And so we have this, again, this kind of suggestion of segmentation between the two events. Because this segment seems to direct tsunamis towards the California coast, there's been some effort to model tsunamis here. The USGS did the SAFIR scenario where they sent a tsunami off the Samiti segment, magnitude 9.1. It caused a 1.2 meter tsunami in Los Angeles, ports of Los Angeles, and about estimated $3.4 billion in damage that would occur from that event. However, based on our work that we've been doing, we've found evidence of ruptures that correlate between sites that span this boundary between the 1964 and 1938 ruptures. So our big question here is, do we need to consider multi-segment earthquakes that would obviously create a much bigger rupture, which would create bigger problems in far-field areas? So just for, we have a lot more sites, but today I'm just going to talk a little bit about Sitkinak Island. So here it is, right at the boundary between the 1938 and 1964 earthquakes. So a perfect place to test our theory about possibly ruptures propagating through this area. So it's in the perfect location to catch tsunamis and land level change because we have this south-facing low-energy depositional environment facing right towards the trench. And obviously the low-energy depositional environment gives us the opportunity to catch those changes in land level from earthquakes. So our studies, what we do mainly is we find these places that we think are good recorders of the changes in land level. So in this case, it was this marsh here. So this is a ridge. We're standing on this ridge looking out over the marsh here. So we basically just set up coring transects that are coast perpendicular, coast parallel. We do a series of push cores mainly, and we could sometimes go down to 4 meters. And we start looking for these changes in lithology. So this is the top of the core here, and we're seeing these changes between peats and muds, which are jumping out at us as possible evidence of land level change, of sudden changes in that depositional environment. So here we are. This is a nice outcrop, which are always great because cores can be sometimes a little tricky. And a big component of our studies is always to survey everything into mean tide levels. So we always deploy tide gauges. In this case, we put one out here, and then leave that out for the 2-3 weeks that we're in the field, and then survey everything into that tide gauge so we know what elevation our marsh is at today and what elevations it was in the past as the land popped up or down. Another really important component of the studies is characterizing the modern environments. If we're going to use microfossils to make interpretations down core, we need to understand where they live today. So in this case, we have our modern transect going from our high marsh, low marsh into tidal flat. And then we've also sampled the modern beach, which is here just in front of our site, to learn more about the tsunami deposits that we might find in the site and be able to match what we see in our site to what was transported possibly by a tsunami. And so once we've wrapped up our study and we have a comfortable understanding of our stratigraphic correlations in the field, we'll choose sections that we think are representative of the stratigraphy. And sometimes we just sample the bank. We also use a Russian peat core to go down and take these samples at depth. A really important part of our work is creating a chronology of earthquakes. So we'll go in and look for stuff to date inside these peats. And if we have an organic peat, we'll often find rhizomes from marsh plants in there that we can be confident that they were killed during the change in land level, for example, right at the contact. And sometimes we find seeds. So we create this chronology of past events. We then do grain size analysis. We do loss on ignition to get an idea of the organic content, again, reconstruct those past environments. And the diatom analysis where we do centimeter resolution diatom analysis down core to see if we can pick up these changes in environment from earthquakes. So this is just an example of what we'll put together when we're back in the lab. We have all our field notes and we plot everything up and try to make these correlations between all the different cores and see what horizons we're confident in that correlate across the site. And we'll take multiple cores. We can't analyze every single one in detail, but we try to do at least 2 or 3 where we go down core, we do CT scanning, we pick out each contact and do dating across that contact. We do the high resolution microfossil analysis. And in this case, we picked out 5 contacts that we thought were sudden changes in environment. So here we had a change from a more muddy environment to a more organic soil above it. Here we had the opposite, from a peat onto a mud, and here we had a mud onto a peat. So as you can see, it's a little more complicated than maybe I suggested at the beginning, where we always see subsidence for every earthquake. So we have our modern diatom data. So across that transect that I showed you before, I went and counted those surface samples. So here's our distinctive tidal flat assemblage at Sitkinak, brackish, fresh and brackish, and our freshwater and fresh brackish. So I have an idea of what diatoms like to live in certain environments today. And then I can take that information down core and count those samples across those contacts of interest, which we've highlighted here, contact 1 through 5. And see how those diatoms are changing. So below contact 5, I see a tidal flat. Above it, I see high marsh diatoms. It's still in a high marsh, and then back to a tidal flat to a high marsh, low marsh to a high marsh, and low marsh to a tidal flat. So we interpreted these as changes in land level related to earthquakes because of the suddenness of the contact and the suddenness of the change in microfossil assemblage. And I didn't put the values here, but we also did the quantitative estimate of these land level changes, which were on the order of about from ½ meter to 1 meter for each contact. So yeah, we have this mixed record. Oh, and then I should have, pointed out that we have, in our record, we do think we see 1964 based on cesium dating, and then the 1788, which was that multiple segment or rupture. So we have this mixed records of both uplift and subsidence at the same site. So we started thinking about how this was possible and created a model that kind of explains this up and down nature of land level change at Sitkinak. So when ruptures stop at Sitkinak, so here's our trench, and here's Sitkinak, it's just a schematic. So we have a little dot of Sitkinak Island. When ruptures stop right at Sitkinak, you have uplift, which is generally along the same distance from the subduction zone at Sitkinak, but because the rupture has stopped here, you actually have this trough of subsidence that can wrap around and create different land level change than you might expect at the site. And this has actually been observed in recent ruptures. So we're pretty confident that this is possible. And this is consistent with 1964, which we see subsidence at Sitkinak, and which also stopped right at Sitkinak. When they propagate through the island, so if you just imagine this blob moving a little bit down, then it's going to be in part of that zone of uplift. So that's when ruptures propagate through the island, you can get uplift at the island. So this suggests that the segment boundary is not persistent and that ruptures can either stop right at the island or propagate through. So in 1964, the rupture stopped right at Sitkinak. We had subsidence consistent with our model. In 1788, the red bar, we have uplift. We also have evidence in other parts of Kodiak that the rupture went through this area. And so we have this evidence now that this rupture boundary is not actually persistent, which is important then to then take into our hazards assessment. So with that information, what are the next steps? So our data actually is now being incorporated into the new version of the hazard maps that are being created for Alaska to consider the possibility of a multi-segment earthquake. And what we've now done, and what I'm starting to do, is now use these results to inform earthquake and tsunami modeling to learn more about the impact of future events. So we need to now consider, instead of just the Saffir source on the Samiti segment, both the Samiti and Kodiak segment that can potentially rupture at the same time. And so what we've done here is model a multi-segment rupture. And for this paper that we're working on, we've actually, we've done the full rupture, but this is pretty unrealistic. This is a very big earthquake. It'd be a very bad day for Alaska and California. But we varied the slip. So we actually have a variety of different ruptures along the two segments. And here's our range of possible tsunami flood heights that can affect the ports of Los Angeles and Long Beach. So now we're taking this beyond Alaska and trying to look out across the Pacific Rim. And we are also considering compounding hazards. So we have sea level rise that's occurring. What is going to happen to tsunami inundation when sea level keeps rising and kind of raises that baseline for inundation? So we have our low emission scenario of 2.6, of worst case scenario 1.5 meters, likely around ½ meter, and for 8.5, worst case of 2.5 meters, likely about 1 meter. And we really need to add this to tsunami inundation heights to get the full picture of what could possibly happen at the ports of Los Angeles and Long Beach. And so this plot here shows the earthquake magnitude that has a 50-50 chance of exceeding certain flood heights as a function of time. And each of these curves is a different sea level scenario. So here today, for the highest historical earthquake that's ever hit the ports of Los Angeles and Long Beach was 0.5 meter. So today it takes about an 8.3 to get to that point. By 2025, a magnitude 8 can do that, just based on a very small amount of sea level rise that kind of raises that baseline. As we consider higher flood heights, similar to the Saffir scenario that I mentioned, so a flood height of 1 meter, today it takes about a magnitude 9. So this is a really rare, big event. By 2090, 2080, we have a magnitude 8, which is a much more common earthquake that can still exceed that flood height if you are including sea level rise. And as you can see, these higher emission scenarios are a much worse case for ports of LA and Long Beach. If you stay with the lower emissions, you don't deal with these higher hazards from lower earthquakes. And then just to finish, something that's 3 times the largest historical flood height. Today it takes a magnitude 9.4, that's a full multi-segment earthquake. If you follow 8.5, so worst case sea level scenario, by 2100, you only need a magnitude 8 earthquake to get to that same flood height at the ports of LA and Long Beach. So I'd like to acknowledge my collaborators who are all paleoseismologists and contributed to this work, but really, and just to bring home this sustainability theme and this interdisciplinary, need to do interdisciplinary work, I want to acknowledge the people kind of outside my field who are really pushing this type of work forward and I think are the future. Thank you.